Any sufficiently advanced technology is indistinguishable from magic.
Welcome, everybody, to a special summertime edition of the Into the Impossible podcast. I'm your fearful host, Dr. Brian Keating, the Chancellor's Distinguished Professor of Physics at UC San Diego, and I'm joined by another distinguished professor from the University of California, Professor Ben Mazin.
I don't think I'm a distinguished professor. I am the Worcester Chair of Experimental Physics, though.
And Ben is in town for a super secret reason that we can't talk about, Jason. But we will. Maybe we will. We'll talk a little bit about that. But I want to expose you to the world of experimental physics, because we don't get enough of that on the Into the Impossible podcast. Because my friends, some of my best friends are theorists, Ben. I don't know.
I'll forgive you.
Yeah. But they write these wonderful books, and very few experimentalists write these books. And because of that, we have a bias, unintentional as it is, towards our brainiac friends, including Sarah Seeger, who was recently in town visiting as well. Now, I want to make the point that there are many branches of physics. There's not only astrophysics, although that's what Ben and I happen to do or specialize in, but within astrophysics, I claim there's no more diverse type of physics that you could do, because you have to do everything, right, Ben?
Yeah, I think in astrophysics, really, it is the mother science. You have all science happens in the universe, right? Therefore, it's astrophysics. So I do think it is the mother science.
And we were talking over lunch about this notion that, kind of the prevailing way that people think about astrophysics is, it just depends on things that are out there. But with the exception of biophysics, although now we're getting into astrobiology, maybe that is a part of astrophysics. So talk a little bit about what you do, the type of sensors and detectors that you make, and then we'll get in and we'll talk about aliens, which I think that you might be forbidden to talk about.
All right, sounds good. So the work in my lab centers around a technology called microwave kinetic inductance detectors, or MKIDs. These are detectors that are extraordinarily sensitive photon sensors. We use them in the optical and near IR where I work because they give you unique advantages over the conventional detector technology, like the CMOS detectors based on silicon that are in your cell phone. So while the MKIDs, these fantastically sensitive detectors that can sense a single photon, tell you the energy of that photon, and tell you when it arrived to within a microsecond, without any false counts, with no read noise or dark current. So while those detectors are the core competency of the lab, it's the application of those detectors that I think is really exciting. So what we do is we take these detectors, we develop them from the ground up. We're very vertically integrated in ways that very few physics labs are. So we do material science to develop new superconductors. Then we do condensed matter physics to understand the detectors and to make them into the best detectors we can make. Then we do lithography and sort of standard semiconductor process or semiconductor type processing to make arrays of these detectors. We then take them in the lab. We do testing on them. We iterate and improve them. And when they're ready, we package them up into a camera, and we build a big camera around them. Then we'll bring that camera to the telescope, and we'll point it at the sky. And the thing that I'm most interested in, the thing that I point at the sky most for, is looking for extrasolar planets. So we're trying to look for planets around nearby stars, and we're doing this using a technique called direct imaging. So most of the techniques for finding planets are indirect techniques, where you look at the influence of the planet on the light of the star. In direct imaging, you're trying to actually take a picture of the solar system. So you're looking at light either reflected by the planets or emitted in thermal radiation from the planet itself. This technique is extremely technically challenging because it relies on a couple very hard things. The first one is something called adaptive optics. So adaptive optics is a technique where you look at a bright star and figure out all the distortions that the atmosphere has introduced into the light that's coming to you. And then you use a rubber mirror, so it's a flexible mirror with pistons behind it, to correct for those distortions thousands of times a second. What you're trying to do is remove that atmospheric turbulence and give you the same kind of diffraction limited image you'd see in space. So that is complicated and has a lot of ways to go wrong. The second thing you need is something called a coronagraph, which blocks the light from the star but passes the light of the very nearby planet. And the third thing you need is a science instrument that sits behind them to collect this information and to do as good a job as possible at distinguishing photons that came from the star versus photons that came from the planet. And that's where my technology, the MKIDs, come in. We currently have a 20,000 pixel MKID camera, the largest superconducting array on the planet, at least maybe until Simon's Observatory comes online, sitting behind the 8 meter Subaru Observatory telescope, behind the Skexeo adaptive optics system and coronagraph. And that instrument is what we're using to try to take these pictures of these extrasolar planets. The long-term goal is to not just to take pictures of these planets, but to use the energy resolution that our detectors have, the ability to tell what wavelength every photon is, to actually look at the spectrum of light that comes from these planets. Now, if we look at the reflected light from the star off a planet, we can look for we can look for changes in the spectra that are imprinted by the passage of the light through the atmosphere as it reflects off the planet. And that can tell us whether the atmosphere is in chemical equilibrium or not. And if it's not, we're going to ask, is that because of life? And so that's one of the things that we're really aiming for. It's going to take another generation of large telescopes for us to get there. We need sort of the 30-meter class telescopes, but that's our goal in the next 10 or 15 years.
And if we had a 30-meter class telescope on another planet, Earth-like in every respect, including brilliant scientists like yourself and your students, how far out could they detect us? How far away in our galaxy could they see us?
So the bad news is we're not going to be able to see from the ground. We're not going to be able to see Earth-like planets around stars like the sun because the contrast ratio, the brightness of the star of the sun to the brightness of the Earth is about 10 billion. And so it's really hard. What we're going to do to make it possible is we're going to look at M dwarfs, which are stars that are smaller than the sun, which means the habitable zone gets closer. And so the contrast ratio between the star and the planet shrinks to something like 10 to the 8, 10 million, 100 million, somewhere in that range. And that becomes doable with our technology. So but because of the planets are so close to their stars, even with the 30-meter telescope, we're probably looking only out at something like 10 parsecs, which is about 30 light years. So it's really just our local neighborhood. You start to need enormous telescopes to look out even farther. The galaxy is very, very big.
Yeah, and the speed of light is very, very slow, at least in some ways, because there was a tweet today from Andrew Radar, I forget how you say his name. I mispronounce it the way I mispronounce your name all the time. And he just did a quick back-of-the-envelope calculation that suggested a grain of sand from here at La Jolla Shores or wherever would impact a spacecraft traveling at 99% the speed of light, maybe 99.9, with enough energy, if you agree with this calculation, of 1/3 of a Hiroshima-class nuclear weapon.
Oh, I can easily believe it. Yeah.
So, not only is the galaxy very big, but the speed of light is slow, and yet it's energetic enough to be dangerous, kind of like I am. But thinking about life in the universe, we've had on a lot of discussions in the past couple of months on this channel and other channels about extraterrestrial technology, etc. First of all, do you believe that there is any kind of sense about asking whether or not there is not only life, but intelligent life, and not only intelligent life, but technological life in the universe? Is that a sensible question?
I think it's absolutely a sensible question. I don't think we have much ability to answer that question, but I grew up on Star Wars and Star Trek like everybody else in my generation, and I'm, of course, fascinated by these questions. I would say that, I can say as an astronomer, from me to you guys, we've looked at a lot of things in the sky with astronomy in a lot of wavelengths: radio, optical, near-infrared, X-ray, gamma ray. And we really haven't seen anything that points towards an origin that is not explicable with natural phenomenon. So unfortunately, I don't think we've seen direct evidence of technological civilizations modifying their environments on galactic scales, at least.
If we did, wouldn't that not change your research direction? In other words, if we had unequivocal Bayesian high confidence credible evidence that there are I know for me it would change what research I do.
Absolutely.
Would impact you.
Yeah, no, I think it would absolutely change at least the flavor of what we're working on. I think my personal opinion, based on very low evidence, is that we're going to find that single cell organisms are going to be relatively common throughout the universe. I figure